going to start with a few disclosures here. Our dear leader and CEO was the person who was supposed to give this talk. He was not able to come, so somebody thought it was a good idea to send me here. Probably Paris sending the French guy seemed like the good thing to do. What they forgot to consider is that my natural habitat is way in the dark corner of the wet lab behind 3 doors of restricted access, so nobody can actually talk to me. So this will be an interesting experience for all of us. We can now jump into trying to answer this question, which is at the core of what Freenome is. And it is, can we detect cancer before it strikes? Can we detect cancer before it becomes a life-threatening condition? So the simplest and still acceptable definition of cancer that I use today is that it is an acquired and local disease of the genome, right? Using this definition allows us to capture all the different shapes that cancer can take, right? In particular, here we see the 4 most prevalent cancers: lung, breast, colorectal, and prostate. Today, cancer is so prevalent that most of us have either direct or indirect experiences with cancer. It is the #1 cause of death in Western Europe and the #2 in the United States after cardiovascular diseases. To give you a sense of how prevalent it is worldwide, in 2012, 8 million people died from cancer, and that is the equivalent of the entire population of Austria. If our technology tool set to fight cancer does not improve in the next decades, by 2032, the World Health Organization thinks that, or estimates that over 13 million people will die for cancer, which is an over 50% increase from 2012. The tool set that is currently available to us for treatment of late-stage cancer or metastatic cancer is pretty rough, right? Today, the gold standard treatments or therapeutics to deal with a stage 4 diagnostics only give patients a less than 20% chance of survival over 5 years. If the patient is thought to be a potential responder to one of the most amazing development of the past 5 years in the fight against cancer, which would be immunotherapy, the survival potential becomes around 1 in 3. If, however, we work towards early cancer detection without any further development in therapeutics, the survival rates start to reach close to 80% to 100% in lung or skin cancer. Those benefits of early detection are actually measurable across most of the cancers, right? From the most aggressive, liver and pancreatic cancer, to, for example, the most accessible ones like breast cancer. An early diagnosis of breast cancer that can be resected, that can be surgically removed, is almost a guarantee of full recovery. Now, the problem is that the existing technology to find cancer early are actually either inaccurate, invasive, or too late. But on top of it, there is over 100 cancer types, and many of them have their own detection kind of technology, right? So even if we wanted to do, we wanted to use today's technology to do pan-cancer diagnosis, it would be an operational impossibility. So we would all spend our time in the hospital getting screened. Beyond this, the technologies are also, with drawbacks, with limitations. The screening for prostate cancer and for breast cancer is suffering from very high false positive rates. Colonoscopy, which is actually extremely precise, is suffering from low patient adherence, it being a very invasive procedure, and CT scans tend to lack sensitivity to early cancer, as well as not being actually a technology that is deployed at large scale to try and detect cancer early. So what can we do, right? How could we detect cancer early, precisely, and across all cancer types? At Freenome, we believe that the answer is in blood, right? The reason for this is that cancers are essentially made up of modified cells, right? And cells to survive need access to nutrients. Nutrients are delivered by blood. And in later stages of cancer, they need larger amount of nutrients to be able to keep expanding, right? The fact that cancer is made up of cells, it means that they will essentially still largely behave like cells. There will be a lot of modification in their behavior, and all those modifications should, in the end, be measurable, right? So cells tend to secrete signals of many different kinds. They can be extracellular vesicles, or they can be soluble molecules. And because tumor cells are behaving differently, those signals should get modified by the fact that some cells in the body are carcinogenic, right? Just as important and not shown on those slides is that the presence of cancer is not lost on the immune system, right? The immune response to the early presence of cancer is also a measurable signal. And the tumor microenvironment, so the cells, the healthy cells that are surrounding the presence of the cancer or the tumor, are also responding and signaling to the cancer that it should try to prevent its growth, right? So there is an entire set of signals that can be measured to try and find the presence of cancer. So Freenome is working towards building a technology toolbox that will allow us to go cancer after cancer after cancer. The core of this technology is to essentially be collecting samples that are representative of the disease that we're trying to go after, to extract and build processes to be able to efficiently extract and measure all the signals that we've just described, and rely on advanced machine learning techniques to be able to essentially extract the required measurements to be able to fully define a health state, right? For example, if we wanted to look for differences between stage 1, stage 2, stage 3, and stage 4 pancreatic cancers, we would set up a set of samples that would be representative of those conditions, and we would be trying to extract the necessary and sufficient set of analytes that allow us to guarantee that a sample would fit either of those categories. So the first piece is to get all of the data, right? So what is here on this slide is essentially the current state of affairs in liquid biopsy. This is a very simplified version of this, but taking blood, separating plasma, extracting DNA, preparing that DNA to get sequencing data is what most companies are doing today. This is inherently limited because this is trying to measure directly the the material that is derived from dying cells, right? For example, in DNA, we can measure methylation patterns, which are known to be associated with many diseases, and cancer in particular. In plasma, there is more than just DNA. We can start measuring RNA, right, of the short, which would be the regulating kind, or the messenger RNAs that will lead to proteins. We can also measure the protein concentration that are also known to be associated with cancer, and many of the tests today are actually relying exclusively on protein concentration measurement. Now, there's still a bit of white on that slide, and there is many other things we can and are measuring that we believe are linked and furthering our ability to detect cancer. What I want to highlight now, and we're going back to the very first process that I described as being the liquid biopsy today, it is a very well understood and widely used process, and the cost of processing one sample is around between $50 and $250 in labor cost only, right? So if we want to process and acquire data across all of those processes, it would simply not be feasible if we were to rely on existing technology. There would just not be enough people in the entire of California to do this. So what is one to do? Well, in 2017, we're throwing robots at the problem, right? So the first step is to actually simplify the process as much as possible. Dealing with RNA or dealing with DNA is actually reasonably similar. And we are, after that, putting in place automated system that allow us to essentially, in a completely lights-out fashion, able to build what we call a data generation factory that would take blood in and generate data in the end. What is shown here is the first stage, and only the first stage of this process, which is being built out at Freenome right now. And it will expand to about 8 to 10 times this size by the time we're done, and able to fully automatically acquire data across all the analytes described in the previous slides. So that's only the first part of the problem, right? So we are now most likely in a position to acquire all the data needed to try and extract the signal that gives us the presence or absence of cancer, right? If we can build out data sets and databases that have partial or total answer to be able to do the initial question of the presence of cancer, we, in the context of trying to go after every single one of the cancers one after the other, want to be operating in a different mode that the field has been stuck in for the past few decades, right? We want to be able to go after cancer at the speed Google is going after apps or features, right? We want to be able to iterate on our data sets and increase the performance of a potential test by working on the data side only. This data infrastructure or the software infrastructure is in support of machine learning algorithms, right? And Freenome is not focusing on developing new models. We are currently focusing on transforming omics data to be able to be used in the most advanced existing machine learning algorithms that have proven themselves over and over again in many different problems. So our challenge is to transform analog and digital measurements into features, into digital measurements that can then be essentially indexed and can be thought of as images, and the same approaches can be used to try and do pattern recognition, right? So this image could be thought of representing a cancer state, right? And if the signal that allows us to detect the presence or absence of cancer is in this data, the pattern should become recognizable, and any new sample that would come for which we would not know the class, we would be able to essentially build an expectation as to whether that sample has or does not have cancer. One of the other most important feature of machine learning is that if we feed it high-quality data, it can learn from more and more data and improve its performance over time, right? And in the context of a clinical test, it is particularly valuable as, you know, in a commercial setting, we would be getting samples in. So this is the first data slide, and I believe this slide to be incredibly hopeful in the context of cancer. So it doesn't look like much, but what this shows is that we are way above chance. The signal that we want to find is there, right? We are able to reasonably well differentiate cancer samples from healthy samples, right? And arguably, we're in the mode where the problem is now not a scientific problem anymore, but an operational problem. We're in the phase where feeding the machine learning algorithm will keep pushing the performance of the test towards near perfection. So all we have to do from now on is to be generating data, fitting into the system, push the performance to a level that would outcompete existing tests, and potentially go commercial. The answer to this initial question of whether we can detect cancer early is most likely yes. If we are now to start thinking about pushing the limit of what those technologies can do, can we find precancerous conditions, right? So it is a less known fact that in cancer, there are many known detectable conditions that are a precursor to cancer. For example, in colorectal cancer, advanced adenomas. In breast cancer, ductal carcinomas in situ. Those are conditions that are detected today and that are well known to be precursor to cancers. So the answer to that question is also yes, and for the same reasons. We are way above chance. We are able to detect the signal that allows us to separate healthy samples from precancerous samples, and by acquiring more data and keep supporting machine learning algorithms, we should be able to keep pushing those systems towards near perfection also. So if we think about this for a second now, we are able to differentiate healthy patients from so precancerous conditions, early cancer, late cancer. So can we actually visualize the progression of disease for a patient, right? So this next few slides will be essentially a case study of a 40-year-old male who has developed prostate cancer and was not diagnosed in time, right? So we're going to look at, over the next 6 or 7 slides, a yearly blood draw that has been run retrospectively through the Freenome test, compared to the gold standard today for prostate cancer, which is a protein test for PSA, right? So the initial draw, sorry, those are called circus plots, right, what we see in the middle, and they're essentially representing the genome in a circle from chromosome 1 to chromosome Y. The links that you see in the middle are translocations, right? They are genomic assemblies that typically don't happen and that link different pieces of chromosomes together. And the blue bars around the circle are essentially genomic counts, or the number of molecules that we've found across the genome that are during our measurements that fall in each one of those positions across the genome. So as we move in time, we see that the second year, there is not a lot of differences, right? The protein level measured by today's test is pretty consistent. The Freenome test agrees. If we keep moving through time, we do see in 2010 a significant increase in the size of the bars in essentially local and focal amplification. There are changes in the genome of that patient that are indicative of a disease forming. Now, in 2011, while the size and the number of translocation is not changing very much, what the Freenome test did by essentially adding many different features, and in this case, the DNA sequence, we were able to find a KRAS mutation, which is a known driving mutation for many different cancers, which in and of itself was almost sufficient to push the Freenome test into a positive result that would have pushed that patient towards further treatment, right? But the protein test itself barely moved. The protein concentration that is today the gold standard for the detection of prostate cancer was still very low, right? And if we keep moving through time, despite the fact that we do not find this mutation anymore, probably because the cancer mutated, what we call the genomic instability, so essentially the sum of the focal amplification and the translocation, in and of itself is sufficient to maintain a positive result from the Freenome test. And unfortunately, this person was only diagnosed in 2015 with stage 4 prostate cancer, metastatic cancer, and passed a few months after diagnosis. So we can distinguish the samples. We can visualize the data. What we can now do is project that information and transform it into a number that we can follow over time, right? We can start thinking about the information that we're generating and the data that we're computing as a measure of distance to cancer, right? Now, being able to detect and measure that distance is not that valuable if we can't do anything with it, right? We've seen at the beginning of the talk that surgical resection are usually an option, but they should be kept as a last measure, and in many cases, surgery is actually not an option. So Freenome is working with a set of pharmaceutical companies to try and develop cures, right? Or at the very least, medicine that would essentially either stop or reverse the progression of cancer, right? So we were focusing in the areas of immuno-oncology and epigenetic modification that we believe are the most promising and the more adapted to early cancer. So if indeed this were to work, we would essentially unlock the last stage of being able to completely transform the experience of cancer. If we can detect cancer early, if we have actionability to stop or reverse the protection of disease, we should be able to avoid many of those genetic diseases entirely. So this is the future that we're trying to build. This is why we get up every day and why we work so hard. And I hope that through this talk, I've given you a sense that this is not only possible and feasible, but likely. Thank you.